Our world is just full of randomness. I mean, think about it. From the stock market going up or down to something as simple as a coin flip. So, how do we make any sense of it? How do we take all that uncertainty and turn it into something we can actually analyze and maybe even predict?
All right, so let's get right into it. The big question is this: how do you put a number on something that's totally random? We need a way to translate all these unpredictable outcomes, heads or tails, rain or shine, into the one language that lets us get a group on them, the language of math. And that is exactly the problem we're going to tackle today.
And here's our hero. The tool that lets us do all this is called the random variable. Now, don't let the name intimidate you. It's really just a simple rule that we make up. For a coin flip, we can just decide, okay, heads is 1 and tails is 0. Or say on a factory line, a product passing inspection is a 1 and a fail is a 0. Just like that, a random event is now a number we can plug into an equation. It's that simple.
So let's start taming some of this uncertainty, shall we? The first step is to get organized. By sorting all this randomness into a couple of different types, we can really start to see its underlying structure. It turns out, random variables really only come in two main flavors. On one side, you've got your discrete variables. Think of these as the counters. They're for outcomes you can actually count up, like how many heads did I get in 5 flips? It could be 0, 1, 2, 3, 4, or 5. See? Countable. On the other side, you have the continuous variables. These are the measurers. They handle outcomes on an unbroken scale, like a person's exact height or the precise amount of time you have to wait for a train.
Let's dive into that first family, the counters. The world of discrete variables is all about these distinct, separate, countable outcomes. And the simplest one of all, the absolute building block, is the Bernoulli variable. It represents a single event with only two possible outcomes. That's it, success or failure, yes or no, 1 or 0. You can think of it as the fundamental atom of probability. And that probability of success, we just call that P. And what's so cool about this Bernoulli is how simple its properties are. The expected value, which is just the average outcome you'd get if you ran this thing millions of times, is simply P, the probability of success. And the variance, which tells you how spread out the results are, is just P times Q, where Q is, you guessed it, the probability of failure. So what happens when you take a bunch of those little atomic Bernoulli trials and you string them all together? Well, then you get a binomial variable. This guy simply counts up the number of successes you get in n independent tries. So we're no longer asking about one coin flip, we're asking how many heads will I get in 10 flips, or out of the next 50 widgets off the line, how many are going to pass inspection? And check this out. You can really see how these concepts build on each other. The expected number of successes, it's just n, the number of trials, times p, the probability of success. It's totally intuitive, right? If a coin has a 50% chance of being heads and you flip it 10 times, you'd expect to get 5 heads. And the variance? That just scales up by n too. Makes perfect sense. Okay, time to switch gears. Let's head over to the other family, the world of continuous variables. This is where we stop counting and start measuring things on a continuous scale. Now, the most straightforward continuous variable you can find is the uniform. I want you to imagine a bus that arrives like clockwork every 20 minutes. If you just show up at a random time, your wait could be anything between 0 and 20 minutes, right? And here's the key. Every single one of those outcomes, whether it's 1 minute or 10.5 minutes, is equally likely. No outcome is special. And because of that, the expected value is, well, it's just the exact middle of the interval. For that bus example, your average wait time would be 10 minutes, smack dab in the middle of 0 and 20. It just makes perfect sense. All right, now for the superstar of the group, the normal variable, famous for its iconic bell curve shape. And this thing shows up everywhere, seriously, from the distribution of heights in a population, to test scores, to tiny little measurement errors in a lab. And there's a deep reason for this, called the central limit theorem, which basically says that when you average a whole bunch of random things together, the result tends to look like this beautiful bell curve. And the beauty of the normal distribution is that you can describe the whole thing with just two numbers. The expected value, which we call mu, tells you where the center of the bell is, the average height, for instance. And the variance, sigma squared, tells you how wide or narrow that bell is, basically how much people's heights actually differ from that average. Now, here's a really important distinction for continuous variables. We can't talk about the probability of one exact outcome because there are infinitely many. Instead, we use something called a probability density function, or PDF for short. And the probability isn't the height of this curve, it's the area under the curve between 2 points. So a higher peak just means that outcomes in that zone are a lot more likely. So you might be wondering, why do we care about all these formulas and definitions? Well, it's because these are unbelievably powerful tools for modeling the real world in all kinds of fields, from weather forecasting and engineering to medicine and, of course, finance. And I want to be clear, this is not just abstract theory. On the trading floor, quantitative analysts, we call them quants, use these exact random variables every single day. They use them to model financial risk, to build strategies that can price complex assets, and to try and make some sense of the seemingly chaotic behavior of the market. This is how they find the signal in the noise. It's how they turn all that uncertainty into a potential edge. Which kind of leaves us with one last big thought. By giving randomness this mathematical structure, we can actually start to predict its behavior. And that makes you wonder, if we can truly model chance itself, what are the ultimate limits of what we can foresee?